Hello, welcome to chapter 4 of the Mediating course book. This chapter includes four important distributions in statistics, namely multivariate normal distribution, chi-square distribution, t distribution, and f distribution. We have already discussed about chi-square, t, and f distributions in our previous lectures briefly. Uh, but now, in this chapter, we are going to include some multivariate aspects of those distributions. But before we start the discussion on those four distributions, there are some prerequisites. So therefore, I'm going to first uh, complete those prerequisites. So therefore, I'm going to first consider mainly three sections, uh, that is types of covariance and their related correlations, and random vectors, and matrix decompositions. These three are required to discuss mainly about the multivariate normal distribution. So therefore, I start my first video on the types of covariance and their related correlations. In this video, I'm going to talk about marginal covariance and correlation, conditional covariance and correlation, and partial covariance and correlation. Actually, I have already done a video on marginal covariance and correlation. That video has this thumbnail. You can find this video on covariance and correlations. So therefore, mainly what I have to introduce in this video is the other two covariances and correlations. That is, those are the conditional covariance and partial covariance and corresponding correlations. But as a complete discussion, I will also include the marginal covariance and correlation briefly. So, as I have already explained in the previous video on the marginal covariance and correlation, we already know that covariance measures the direction and magnitude of the linear association between two random variables. One weakness of that quantity, that is the covariance, is that its numerical value depends on the units in which the variables are measured. So therefore, if you have two data sets, the units are different, therefore it will be difficult for us to compare the covariances. So as a solution to this problem, usually when you want to talk about the direction and magnitude of a linear association between two variables, we talk about the correlation instead of the covariance. Of course, correlation is defined using the covariance. So therefore, we have to talk about the covariance first. But usually as a measure of the direction and the magnitude of the linear association, usually we use correlation. So correlation is a standardized covariance. So we standardize the covariance by dividing the product of the two standard deviations. It is dimensionless. In other words, it's units free. And provided that the relevant variances are positive, that means not equal to zero, correlation takes values between -1 and +1. So that is what we have already seen about the marginal correlation. That is also called usually the Pearson's correlation. So the marginal covariance, also called the unconditional covariance, measures the overall linear association between two random variables, say capital X and capital Y, without controlling for any other variables. It is defined by the expected value of the products of the differences between the random variable and the corresponding expected value. Right? The usual notation is sigma. Sigma xy we use to denote the covariance between x and y. So it's equal to expected value of x minus expected value of x times y minus expected value of y. And we can show that this is also equal to expected value of x times y minus the expected value of x times the expected value of y. So the corresponding marginal correlation, also called unconditional correlation or also called Pearson correlation, is defined as covariance between x and y divided by the product of uh, the two standard deviations. So it is denoted as rho xy. It's equal to covariance between x and y divided by the standard deviation of x times standard deviation of y. Right? Square root of the variance of x is equal to the standard deviation of x, and square root of the variance of y is equal to standard deviation of y. So therefore, it is defined, it is given by this formula, sigma xy divided by sigma x times sigma y. The marginal covariance and marginal correlation describe the association in the joint marginal distribution of x and y. Any other variables are ignored or integrated out. Now let us look at the next type of covariance and correlation, that is conditional covariance and correlation. The conditional covariance of x and y given random variable z is defined by the expected value of x minus the expected value of x given z times y minus the expected value of y given z for all given z. Right? In other words, this is the same as expected value of x times y given z minus expected value of x given z times the expected value of y given z, and that is denoted by sigma xy given z. Right? That is the notation that I will use for that conditional covariance. So the conditional covariance describes the linear association between x and y within the conditional distribution determined by z. In general, covariance of x and y given z is a function of this random variable z, and therefore it is a random variable. In particular, if we talk about the covariance between x and y given capital Z equal to some value simple Z, in that case, covariance between x and y given capital equal to simple Z, capital Z is equal to simple Z, is going to be a function of simple Z. It's a function of simple Z in that case. So the corresponding correlation is called the conditional correlation. It is defined as the conditional covariance between x and y given z divided by the standard deviation of x given z times the standard deviation of y given z. In other words, that is equal to sigma xy given z divided by sigma x given z times sigma y given z. And that correlation, conditional correlation between x and y given z is denoted by rho xy vertical stroke z, vertical stroke to indicate the given. Right. So for a particular value, capital Z equal to simple Z, right? That is when this particular event has happened. This correlation will be in that case, rho xy given Z is equal to Z, simple Z, which will be given by sigma xy given Z is equal to simple Z divided by the standard deviation of x given Z is equal to simple Z and standard deviation of y given Z is equal to simple Z. So in that case, it will be a function of simple Z. So the conditional correlation may vary with simple Z in general, therefore. Consequently, it need not to be a single constant. So that is understood. And we have seen this kind of situations in the previous examples when we are looking at conditional expectation, conditional variance, so on as well. Then the third type of covariance and correlation that we will consider here are the partial covariance of x and y controlling for z. That is the covariance between the residuals obtained after removing the best linear predictors of x and y based on z. In other words, let us say Rx is the residual vector when we regress x on z. When we find out the best linear predictor using the least squares regression. So therefore, according to our definition that we have discussed under regression in a previous video, is equal to x minus the predicted value, right? The value, predicted value of x given by the fitted regression line. And similarly, Ry residual in this case will be equal to y minus the predicted value based on z, predicted value of y based on z. Right. So now if we look at the correlation, covariance between these two, that is called the partial covariance, covariance between Rx and Ry. Right. So that is denoted by sigma xy dot z. No, please remember in the previous situation when you look at the conditional covariance, it was denoted by sigma xy vertical line to indicate given and then z. This one is denoted by sigma xy dot z. So that is the covariance between x and y dot z. Mathematically, it is equal to the covariance between Rx and Ry. Where Rx is the residual after regressing x on z using the least squares method, and Ry is the residual after regressing y on z using the least squares regression. Then the corresponding partial correlation is the correlation between the same residuals, right? So therefore, that is denoted as rho xy dot z, that is equal to the correlation between Rx and Ry, and that will be equal to sigma xy dot z divided by sigma x dot z times sigma y dot z, where sigma x z is the standard x dot z is the standard deviation of Rx. And sigma y dot z is the standard deviation of Ry. Right. And we can show that actually this quantity can be written in terms of marginal correlations as well. Uh, is that formula rho xy dot z is equal to rho xy minus rho xz times rho yz divided by square root 1 minus rho square xz times 1 minus rho square yz. So that expression we can obtain using the by substituting the expressions for these ones. But I'm not going to derive it here. Just we are going to accept that is as a correct formula. So the partial covariance and partial correlation measure the remaining linear association between x and y after the linear effect of z has been removed from both variables. So, for example, there can be a situation where x and y both are depending on z and some other variables, for example. Right. So, after removing the linear effect of z on x, there may be still some other linear effect remaining on x uh, based on the other variables. And similarly, after removing the linear effect of z on y, there may be still remaining linear effects of other variables on y, right? So this partial covariance and correlation measure the remaining linear association between x and y, right? After the linear effect of z has been removed from both variables separately. So for a collection of control variables represented by a random vector z, as I mentioned, if there are several other variables in z, say, for example, uh, earlier in situation, we considered only one z, one variable. But in general, z may be a vector, for example, vector of several other variables, right? In that case, we can talk about covariance between x and y dot vector z. That means that will be the covariance between the residuals coming from the regression of x on this z, right? There are several variables in z, and the residual coming from the regression of y on z. So the conditional variance and conditional covariance and partial covariance are generally not equal. Right? They don't have to be equal. They can be different. Conditional covariance describes the covariance within the conditional distribution, whereas the partial covariance uh, gives the idea about the linear relationship after removing the removing the linear effect of a third variable, right? Or third vector of variables. So now to get some idea about these things better, let's look at some examples. The first example I'm going to consider three random variables. Say X is the systolic blood pressure, Y is daily sodium intake, and Z is age. Suppose we know that there are pairwise correlations are given by these numbers, rho xy. These are the marginal correlations, so Pearson's correlations. Rho xy is equal to 0.6, rho xz is equal to 0.7, rho yz is equal to 0.5. Let's say those are the values. Remember, these are not the sample quantities that we have been discussing all throughout this slides. We are talking about the theoretical quantities, right? Population quantities. So according to these numbers, now we can show these numbers in corresponding correlation matrix like this. Correlation between x and x is equal to 1, correlation between y and y is equal to 1, correlation between z and z is equal to 1. The other correlations are in the off diagonals. For example, this is the correlation between x1 and x2. This is the correlation between, sorry, in this case, x and y. And this is the correlation between x and z. And similarly, this will be this is a symmetric correlation matrix. Now, let's look at the marginal correlation between x and y. And later on, we will look at the conditional correlation between x and y given z, and also uh, that we will not be able to calculate it, but we can discuss about it. And then we will also calculate the partial correlation between x and y given z. Right. So the marginal correlation between systolic blood pressure and daily sodium intake according to this problem is rho xy, that is equal to 0.6. So what does that indicate? This correlation describes the relationship between blood pressure and sodium intake without considering age. In this case, we have considered only three variables. The third variable is age. In this case, we are considering the theoretical correlation, Pearson's correlation between x and y without considering age. Thus, the population as a whole, people with greater sodium intake tend to have a higher blood pressure, and this correlation seems to be somewhat moderate. However, age may be related to both blood pressure and sodium intake. Or maybe it's related to only one of those. That's also possible. Therefore, a part of the marginal association between x and y may be explained by age also. So we will understand that when we look at especially the partial correlation. But before that, we will also look at the conditional correlation. In this case, using the given information here, we cannot calculate the conditional correlation. If you want to calculate the conditional correlation, we need further information like the joint distribution of x, y, z, because in this case we have not considered any joint distribution, any model for the joint distribution, and we cannot actually calculate the conditional covariance. But we can just talk about, for example, if we are interested in the correlation between x and y given z is equal to 60, that means in that case, we will be considering the Pearson's correlation, for example, between x and y for those whose age is 60 years. So conditioning on the fact that z, the age is equal to 60 years. So the conditional correlation also may vary across age groups. So the conditional correlation between x and y when z is equal to 60 is not the same as, in general, it doesn't have to be like that. The conditional correlation between x and y when z is equal to 40 or 70. It's going to be generally depending on whatever the value of z that we are considering. Now let us look at the partial correlation. We can actually calculate the partial correlation in this case because we know the marginal correlations, and we have a formula to calculate the partial correlation using the marginal correlations. Right. So the partial correlation in this case will measure the linear relationship between blood pressure and sodium intake after removing the linear effect of age from both variables. The partial correlation between x and y controlling for z is given by this formula here. So if we substitute the marginal correlations that we have in this formula, we get 0.404 as the partial correlation between x and y when Z is after controlling for Z. So we can see that this value here is less than the marginal correlation. Marginal correlation was zero point 0.6. This one is 0.4, right? So after removing the linear effect of age, the correlation between blood pressure and sodium intake decreases from zero point 0.6 to approximately zero point 0.4. Thus, the reduction from zero point 0.6 to zero point 0.4 can be explained as follows. That means a part of the observed association between sodium intake and blood pressure is due to their common positive relationship with age. After this age-related component is removed, only a weak positive linear association remains between X and Y. In other words, a part of the marginal correlation between X and Y can be the observed association, marginal association between sodium intake and blood pressure, may be due to their common positive relationship with age. So after removing this part of the linear association, there is a weaker linear association between the remaining, after removing the effect of age, the remaining residuals will have only a weaker linear relationship. In this example, age is best regarded as a confounding variable because it is related in this case to both of the other variables. Right? Age is the Z variable. Z is related to both X and Y generally, right? So therefore, it's a confounding variable, right? It's possible that uh, sodium intake depends on age, and blood pressure also depends on age. Now, I have looked at a sample equivalent of this thing. Remember, I told that these things that we are discussing here are not sample quantities, right? When you say correlation here, correlation between X and Y, theoretical or population quantities. But just to get an idea, what I look at is I generated some data uh, to have approximately these theoretical correlations in the data, right? So we will look at an example using those generated data, right? So I have generated some data, and actually there are correlations, the correlations between X, Y, and Z, the correlation metrics in the generated data is almost exactly the same as the theoretical one that I wanted. So here is the graph that of the generated data, right? Here what I have done is I have considered, I have divided the age into several groups, right? Instead of considering individual values, I will just look at some small groups. So they are depicted here with different colors. For example, youngest age group is denoted by blue, oldest age group is denoted with this violet color. So there are mixed with, but most of the younger ones are here, and most of the oldest ones are here. And when you put all those things without considering age, this whole scatter plot will be considered as one scatter plot. And then if we calculate the correlation here, the sample correlation coefficient also came as 0.6 approximately. And then what I did was I regressed both X and Y separately on Z, and then took the residuals. And then this is the residual Ry versus Rx. And in that case, the correlation coefficient is 0.4 approximately. Right. So we can see that in this case, for example, for these blue ones, there may be one type of correlation. And for the red ones, another type of another value actually, right? For the correlation, right? So the correlation actually depends on age. Correlation between X and Y depends on age. But if we ignore age, then you get R equal to 0.6. Right? But when you remove the effect of age on X and Y separately, then according to this thing, there is still some linear association remaining between X and Y. That is probably because one reason may be the correlation between X and Y also depends on some other variables that we have not considered here. Right? Age may be one variable, maybe there are some other variables, right? So therefore, still there is some linearity, linear effect with those variables are remaining. That probably that is why uh, the partial correlation is only reduced by only a small amount. Still, some linearity between X and Y is a weak relationship, but still some linearity exists. Right. Let's look at another example. Suppose students with higher prior ability generally need fewer study hours. Prior ability also improves examination performance. Consequently, the positive effect of studying can be hidden when prior ability ignored. So here we are going to consider three variables again. One variable is uh, the amount of studying. The second variable is the uh, examination marks, for example, examination performance. A third variable is prior ability. Right? We know some students are uh, uh, more kind of able or intelligent than some other students, right? So those intelligent students don't generally require to study as hard as the other students, right? But still they get higher marks, right? But if we just ignore their prior ability, we can look at the marginal correlation between the number of hours, for example, they studied and the examination marks. In that case, we will be looking at the marginal correlation, right? So here again, I have some generated data because these are not theoretical things. If you want to talk about theoretical values, we need to have some idea about their joint distributions as well, right? So suppose the marginal correlation between marks and the amount of studying is equal to in this case, marginal correlation is 0.06, very weak. Why is that? Partial correlation controlling for prior ability is 0.794. So this is an example uh, uh, opposite to the previous situation. In the previous situation, marginal one was larger and the partial one was smaller. In this case, marginal correlation is smaller and partial correlation is larger. That is possible. Let's see how that has happened by looking at the graph in this case, right? So here is the original data, the scatter for the original data. Here, again, there are several colors indicate the prior ability level, right? So this group in blue is the lowest prior ability group. This group here in violet dots is the highest prior ability group. Now we can see that if you consider these groups separately, you can see there is a linear relationship between study hours and the examination score. for this group, some correlation. And similarly, for this red dots, which is a high ability group, there is a different correlation, and regression line would be different also. And for this group, there is a different correlation and so on. But if when we ignore the prior ability, we have to put of them together. In that case, you can see there is almost no correlation if you look at this picture taken as a whole, right? So that's why the marginal correlation is very, very small here, right? But of course, individual correlations can be high here, right? This high, this is high, and so on. So when you uh, regress each of these variables on the prior ability level, you will get residuals. And this is the scatter plot of residuals after removing the prior ability effect from the examination marks. This is the residual after removing the prior ability effect from the study hours. Right. So we can see that now there is a very strong linear relationship remaining between examination score and study hours. So that shows that there is, of course, actual strong relationship between study hours and the examination marks. When the study hours increases, examination marks increase generally on average. But when it is mixed with the prior ability, you cannot distinguish. You cannot see that high correlation. Right? So therefore, if you want to see the high correlation in this case, you have to remove or take the effect of prior ability into account, right? So taking into account is one method is this one, that is regress on that one, and then look at the residuals after removing the effect of this prior ability, right? Or in other words, in regression, what you can do is instead of fitting a regression line to the whole data set, you can consider prior ability as another variable, include that one into the model. So in that case, your model will be more suitable, right? So in this case, the prior ability is related to both study hours and examination performance. But the thing is that the prior ability is negatively associated with the study hours. Students with higher prior ability generally spent a small number of hours for studying. So there is a negative association between the prior ability and the number of study hours. On the other hand, prior ability is positively associated with examination performance. Examination is performance higher of those who have higher prior ability, right? So that's why when you put them together, it's like cancelling off those two, not exactly cancelling off becoming zero, but some part of that correlation uh, becomes very, very, very unclear because of that. There's a positive and negative correlation in the same picture. So therefore, prior ability can be regarded as a confounding variable in this case also. Confounding variable is a variable usually which is related to all the other variables that we consider. In this case here, we are considering two variables to look at the correlation now. So X and Y are the two variables. If the third variable is related to both of these variables, then the third variable is called a confounding variable. So in that sense, prior ability is negatively associated with study hours, and also the prior ability is positively associated with examination performance. So that means prior ability is related to both of the other X and Y variables. So that's why we call it a confounding variable. In this example, the marginal correlation is close to zero because two relationships operate on opposite directions, as I explained here. So more study hours are associated with higher examination scores. Students with greater prior ability tend to study fewer hours while still obtaining higher examination scores. The second relationship conceals the first relationship. Consequently, when prior ability is ignored, the marginal correlation gives the impression that there is a little relationship, there's a little linear relationship between study hours and examination scores. So that is a common thing when there is a common possibility when there is a confounding variable. Right? Once prior ability is controlled, the strong positive relationship between study hours and examination scores become visible. Thus, the final conclusion is among students with the same prior ability, greater study time is strongly associated with the higher examination score. Let's look at another example. Right? In the previous examples, the third variable was a confounding variable. We were looking at x and y, relationship between x and y. In the first case, ignoring is it, that is marginal. The other one, after removing the effect of z, that is the partial. Now, in this case, z actually plays a different role. Let's look at the example first. Suppose a company records information about its online advertising activities over 200 weeks. For each week, the company records the following three variables. X is the advertising expenditure. Y is the number of online purchases. Z is the number of visits to company's website. Advertising expenditure is X. Y is number of online purchases. Z is the number of visits to the company's website. Right. So again, this is an example with some generated data. It's not a theory. We are not dealing with theoretical situation here. So we are looking at the corresponding sample quantities actually. Here we are looking at the marginal correlation. Suppose the marginal correlation between x and y is equal to 0.57, approximately 0.6, and the partial correlation after controlling for website visits is negative 0.0, is almost zero, right? So let's look at the data and see how this kind of thing can happen, and also what is the role of variable z in this case. Right. So this is the overall picture before removing the effect of z. So again, number of website visits I have categorized into several groups with different colors. Blue indicates the lowest and uh, the purple indicates the highest level. Right. So overall, it looks like that there is some positive linear association between the number of online purchases and the amount of advertising expenditure. Right. Now you can see here there is some relationship, positive relationship for the lowest website group, and probably there is another type of linear relationship, a different one than this one for the highest website group, and there may be some other relationships, linear relationship or very weak linear relationship for the other groups. Right. So anyway, after taking the website visits variable z into account, that means after regressing x on z and y on z, when you're considering the residuals, this is the scatter plot of residuals coming from y and residuals coming from x here. And we see that there is almost no linear relationship, right? Very, very weak linear relationship given by this is negative, even though it says negative, is almost 0.08. So what happens here? The marginal correlation between advertising expenditure and online purchase describe their linear relationship without controlling for the number of website hits. The first graph shows a moderately strong positive marginal correlation, actually linear correlation, right? Was moderately strong. Thus, weeks with great advertising expenditure tend to have more online purchases. Uh, the number of website hits is depicted with different colors here in the graph, as I shown here. Right. So the partial correlation describes the linear relationship between advertising expenditure and online purchase after removing the linear effect associated with website visits from both variables. So after removing the linear relationship with the number of hits, there is almost no linear relationship remaining between X and Y. So that means when you regress on Z, regress X on Z and regress Y on Z, almost all the existing linear relationship is removed, and there will be no remaining linear relationship between X and Y after removing that effect. So that's what has happened here. An advertising expenditure residual indicates whether the company spent more or less on advertising than would be expected for a week with that number of website hits. Similarly, an online purchases residual indicates whether the company obtained more or fewer purchases than would be expected for a week with that number of website visits. The second graph shows that the partial correlation is close to zero. Therefore, after controlling for website visits, little linear association remains between advertising expenditure and online purchases, because both of those variables are highly related with the previous uh, two variables somehow. But the way that it is related is not the same as in the previous situation, as we will see in the next slide. The considerable reduction from the marginal correlation to the partial correlation is consistent with the following explanation here. This is the explanation given here. Great advertising expenditure generates more website visits, and the increase in website visits subsequently results in more online purchases. Therefore, website visits may act as an intervening or mediating variable in the pathway. So actually this variable, the Z variable is in the mid of the two other variables. Right. So we can show that relationship like this. Advertising expenditure is highly related because website hits increases on average when the advertising expenditure is increased. And then online purchases increases as the website hits increases. Right. So the marginal correlation includes the indirect association operating through website hits. Right. Marginal correlation between these two includes the indirect association operated through the website visits. Controlling for website visits removes this part of the association, and consequently the partial correlation becomes much smaller. However, the difference between the marginal and partial correlation alone does not prove that website hits mediate the relationship. Right? There may be some other variables also impacting on this marginal linear relationship. For example, the timing of the variable, the study design, and possible alternative explanation must also support the proposed causal pathway. Right. So just because we cannot say there is a causation here, right? Causation because number of websites are increased caused by this one directly, and this is increased by this thing directly, we cannot say still from this experiment, this observation, though this is an observational study, but there seems to be some mediating association, right? This variable is is acting as a mediator between these two variables. So that is the end of the discussion about these three types of covariances and correlations. In the next video, I will discuss about random vectors, right? Because this idea of random vectors and their means and variances, covariances are important, especially when we talk about the multivariate normal distribution. And there is another important concept that we require is that is the uh, decomposition of matrices. So those two topics will be discussed in the next video.